Okay, we're now going to look at collisions and momentum, which is a bit of a recap from last year. So let's look at Newton's laws again. So the first law is this idea that an object's velocity will stay the same unless the force acts. This idea of inertia. Something with more mass actually has more inertia. So we've done that one last year. Okay, so velocity stays the same unless an unbalanced force acts. It just tends to keep on doing what it's doing at rest, stays at rest. Don't forget also then that if it is an unbalanced force or a net force or an overall force or the total force, you are going to get acceleration, so that's going to change the situation. And the size of the acceleration depends on the force, it's directly proportional to the net force, and inversely proportional to the mass. So a bigger force gives you a bigger acceleration, and a bigger mass gives you a smaller acceleration. And you can use that as F equals ma or A equals F over m. We will look at one as F equals change in momentum over time as well as another way of working that out in this topic. All right. Finally, you've got the idea that if there's a force acting on one body, there will be an equal and opposite force back on the other body. So it's on two different bodies, equal size forces, and in opposite directions. Some people just call that action equals reaction, which is a very loose way of saying it because it doesn't describe the full law. So common sort of question would be if you've got some sort of a wall or an object and a ball was to come and collide into it with a certain mass and a certain speed, and it collided elastically, what does that mean? Well, elastically means it doesn't lose any kinetic energy. So it's going to rebound there, and I'm putting it down a bit so we can actually see what's going on, with the same speed, 5 meters a second, but back that way. So it's coming in and it's going to bounce back out that way. And I'm going to hit this at 90 degrees, by the way, a 90-degree angle. Okay? So based on that, could you work out some basic things? So typical questions would be, 1, what's the change in velocity of the actual object? 2, what's the acceleration on the ball? Now we probably need to know how long it's in contact with the wall for that. So let's say it's in contact with the wall for 0.1 of a second. Okay, so could we work out the acceleration of the ball when it's actually colliding with the wall here? Thirdly, could we work out the force on the ball when it's doing that? Okay, so let's start with that. So change in velocity, we will be doing delta V equals V dash take V. Now you could do that as Vf final, take V initial, or you could do it as V2, take away V1. As long as you get the idea that it's this one, the final one here, take away the first one. Okay? So if you just went, oh, it's 5, take away 5, you're going to get 0 here, you would be wrong. So be careful with that. Because you've got to remember velocity is a vector. And if it's a vector, we need to consider the arrows here. So let's try this again here. I'm just going to do it from this point of view. So try again. Let's draw it. V dash is actually 5 to our left. Subtracting a V going 5 to our right. So this is not going to be 0 because they're not in the same direction. So if you look at it, subtracting a vector, you would normally add it in the opposite direction. And that actually shows you we're going to get 10 meters a second as a total change there to our left. So there's a big change there. You actually had changed the velocity by stopping it, and then you've actually added a change in velocity by pushing it that way as well, and actually increasing the velocity that way. So you've stopped it and turned it around. Now that actually has some implications later in terms of you get more force if you actually reverse the object rather than just stop the object, because you get twice the change in velocity. But we'll come back to that. Now the acceleration here is rate of change in velocity. So if it's 10 meters a second to the left here, and it took a time of 0.1 seconds, that's going to give you 100 meters per second going to our left. Okay? So that's the acceleration. Now if you know the acceleration, you can use Newton's second law to work out the force, because F equals ma. There's a force acting that's caused that acceleration. Now we need to know the mass, it's 2 kilograms, and we've got an acceleration going of 100, so you get 200 newtons going to the left on the ball due to the wall. Okay? So that's a fairly standard routine. Can you work out change in velocity? Therefore we know the acceleration of the ball while it's in contact, therefore we know the force that the wall exerted on the ball. Now one last question could be then, to use the third law, what would the force on the wall be during this collision? Alright, now according to the third law, if there's a force acting on one object, there should be an equal and opposite force on the other. In this case here, it should be 200 newtons to the right because of the third law. Okay, it should be equal and opposite to the force on the ball, so minus the force on the ball. So therefore it's 200 newtons to our right. So that's a typical question. The harder one comes when we want to actually try this again, but this time have the ball coming in at an angle. And how would that change, even if it's an isolated collision, but you actually knew what the angle was there. We gave it an angle here of maybe 40 degrees or something. How would that change what actually happens? So it involves a bit of trig when you do the vector diagram for this. So you'll find parts 2, 3 and 4 do not change. This is the part that gets harder, the change in velocity. Because if you look at this then, so if we try this again with this different sort of arrangement, we've got to actually try and do change in velocity is v dash take away v again. And don't forget this is your v dashed here, the 5 coming out. We've got 5 coming out this way at a certain angle of 40 degrees in there, minus 5 coming down this way at an angle of 40. And you just have to be really careful about the vector diagram now. So you need to be careful here. Don't forget you need to reverse this second one. This is plus 5 that way then at 40 degrees. Okay. So we need to do vector diagram of this. Most people will just go and do it as that way plus that way then. Go and do it like that. So there's your change in velocity there. There's your 5. There's your 5 because this is VF. That's minus VI. Okay. And there's your change in velocity. And don't forget we actually know this is 40 degrees in here. And this will always be an isosceles triangle here, at least with two sides the same. Sometimes it might actually be an equilateral if these are all 60s. But you can be guaranteed that these two angles will be the same here. Okay. And looking at that then, how would you work out change in velocity? You could do this. A squared equals b squared plus c squared minus 2bc cos theta, if you've actually been doing your trig that way. The other way to consider this though is to do this as a triangle on 1/2 here with a right angle and focus on that part there. So what you've got here is you've got a triangle, we're trying to find this value out here. We've got a 5 there and we've got a 40 in there. So this is very much like a flipped horizontal component for projectiles. And if you were doing that, you would have gone v cos theta, wouldn't you? And this is the same thing here. And that x value there will be v cos theta. And obviously if you double that then, you will get the full change in velocity. So the change in velocity here will be change in velocity is equal to 2v cos theta. So 2 times by 5 times by the cosine of 40. And you get 7.7 meters per second. To the left is the change in velocity. That means the other value is going to be smaller because the last one was 10, wasn't it? So the acceleration that we do change in velocity on time is going to be smaller. The force on that ball must be smaller, and therefore the force on the wall is actually smaller because it's more of a glancing blow. It's always going to be smaller if you're not at 90 degrees. That's when you get the maximum change. So looking at Mr. Aguirre's PowerPoint here, it covers it very well. You've got your 3 laws you need to be aware of in this section. The first law of inertia, the second law of what happens if there is a force acting and accelerations occurring, or vice versa. And the idea that you'll get the forces always in equal and opposite pairs on different objects. Okay? So you can actually work out the acceleration of an object by working out its change in velocity. It applies at 90 degrees, and here's used VO and VT here, but you can use V dashed and V. And it's the change in velocity over the certain time period. Here, they've used 20, so it's going to be minus 20 because it's coming to his left. Take away the 20 going in. So altogether, you'll get minus 40 there. All right, but you can use arrows instead if it suits you better. Based on that, you can work out the acceleration. If you know the acceleration, then you can use Newton's second law to work out the force based on the mass of the ball, just F equals ma, and it's got a direction to the left, away from the wall. And the third law will then tell you that the ball must have a force on the wall exactly equal and opposite to that, of 400. And obviously that changed if you come at an angle, because the change in velocity will end up being smaller when you check the vectors for that. So you've got 2 components here that you can work on. You've got a VT out that way, and you've got to do minus VO. So minus VO will be back in the opposite direction there. You can add that tip to tail. Change in velocity is there. And we've already talked about 2 ways you could actually use to work out the change in velocity. And then the rest will be the same. So that's the example I've already gone through, that sort of typical one there. And they don't get much harder than those. Okay?